Hello and welcome to the second and final part of our final year project presentation. Let us start by meeting the team. My name is Kevin Jemail and I worked along with my fellow teammates, Ali, Hassan, and Mohammed, along with our project advisor and mentor, Dr. Wasim H. Habchi. Today we are going to talk about how we designed a manual pipe cold bending machine from A to Z. The outline was based on the methodology we followed starting. 1. A brief introduction on bending and its types that were included in the literature review. 2. Then move on to the project constraints that led us to formulate a problem statement. 3. After that, a preliminary machine designed to meet the constraints guiding us to formulate our first simulation. 4. Then this simulation was done to estimate the required force and torque to achieve the constraints. 5. After obtaining the simulation we used these results to design a 3D model of the machine using SolidWorks. 6. Upon completion a static simulation was done on critical parts of the machine ensuring their safety factor. 7. Later cutting lists and drawings were generated to initiate the manufacturing phase. 8. Finally we are going to end our presentation with a conclusion stating the main findings and results. So let's start with the introduction. Cold bending refers to all types of bending that does not use any added heat to bend the pipes. The procedure is usually performed by wrapping a pipe or other material around a die or shape that causes the pipe to bend. As mentioned before, we talked about the definition of bending. Here we can see press bending. Its advantage is that it gives shape to the object. Moreover, compression bending is less expensive for tooling. However, the one downside of compression bending is that it is not intended for small tight radius bends. Now for stretch bending, its disadvantage is that it does not keep the same cross section for tubes while bending. Finally, for roll forming, it can produce more parts with greater uniformity and consistency throughout the length of the part. Proceeding to the problem statement. The objective of this machine is to bend steel or copper pipes with an outer diameter of 5 cm and a thickness of 5 mm. Moreover, it should include a bending angle ranging from 0 to 180 degrees and a bending radius of curvature of 10 cm. All these to be obtained manually with a human input force of 100 newtons, which is equivalent to around 10 kilograms or 9.81 kilograms to be more precise. As shown in the tables, after comparing the yield strength of both material we deduced that carbon steel had a higher yield strength, thus a higher force is needed to reach the same constraints. So, we based our future simulations on steel. After making sure that the 3-roller bending type of machine can reach the desired constraint, it was approved, and we proceeded to the basic machine geometry. The figure on the left demonstrates the dimensions of the roller. All 3 rollers have the same dimensions. We can see that the groove has the same diameter as the pipe to maintain the pipe's cross-section, avoiding wrinkling and ovality while rolling. The spacing between the rollers is chosen to be 400 mm, enabling the 3 rollers to be coincident once aligned. And on the right the exact relative position of each roller is also shown. 122 mm represents the maximum displacement needed to obtain the required radius of curvature. The design was considered efficient because the upper roller did not have to go all the way down to achieve the required radius. This is how it was calculated. On the left the geometry constraints were drawn to calculate the roller size and relative position. This drawing helped in relating all the variable parameters and visualizing them in 2D, helping us to convert it to a mathematical model shown in figure B. On the right the y-axis represents the displacement of the top roller moving downwards. As the displacement is close to 0, the radius of the workpiece asymptotically approaches infinity. We realized the relationship of the displacement is not directly proportional to the radius, but it is exponentially related. The more the displacement increases, the smaller is the radius. An interesting point is illustrated showing that the minimum radius that can be achieved is 125 mm, after several trial and error iteration for the roller radius. In the interest of time, we will not be going into the details of the equation. After deciding on the geometry that was just illustrated, we could now simulate the rolling process with known dimensions to estimate the input force and torque required. A nonlinear simulation was needed because we were plastically deforming the workpiece, surpassing the linear elastic region. The geometry was made on SolidWorks and imported to deform. The rollers were assigned as rigid bodies because they were not a subject of interest. The workpiece was considered as a slave and the rollers as the master. AISI 1035 cold-drawn steel was assigned to the workpiece. Moreover, friction, creep, buckling was accounted for. The first graph shows in light green illustrate the downward movement of 3 mm of the top roller, and the dark green shows an input angular velocity of 1 rd/sec to achieve 2 full rotations. In the figure below, the predicted force starts to increase linearly until reaching the yield strength point A, which later follows a prescribed curve that is analytically made through a dog bone test. The displacement at this point is very small, that is why it is not showing clearly in the animation. After reaching the maximum displacement, the maximum force turns out to be 189 kN, which is equal to around 18.9 tons reaching point B. A sudden force drop is witnessed at point C in the small period just after the vertical display CM1 ent and before initiating the start of the rolling process. It is advised to interpret the result while simultaneously looking at the figure above. Once rolling starts, the vertical force needed goes back up to point D, remaining at an almost constant value. The cycle is repeated 4 times. The torque was predicted using the same process, and it increased until reaching 450 Nm every time the rolling starts. This figure shows the contact sets, kinetic friction of 0.13, and static friction of 0.45 between the workpiece and the rollers. All these generalizations are made based on the predicted results by Deform 3D. Here we can see the main drawback visualized after running the simulation. There the ends of the workpiece cannot be rolled, and we get unwanted dents at each end too. This figure shows a visual demonstration of the mesh and the strain done to the workpiece. A pyramidal mesh was generated, and after each iteration the workpiece was remeshed. Based on the 18.8 ton force and 450 Nm torque, we can now start by modeling the rest of the machine components. UPN or welded housing supports are pinned to the UPN. Bearings are placed in the housings. The shaft holds the bearings from one side and cap holds it from the other. 2 sprockets are connected for the bottom roller to rotate together. An additional sprocket is inserted that will be later connected to a gearbox. The pins hold the bearing in the housing. The plates were designed to fit with specific tolerance to fit between the UPN. As you can see, bolts and nuts hold the shafts and bearings in place, keeping them from sliding while rolling. Analysis simulations are made with SolidWorks with material configuration conforming to American Iron and Steel Institute AISI standards. Simulations are made on critical parts of the machine, which include the shafts and the top plate. The force results in 335 megapascals stress on the top and bottom regions where there are sharp cuts. This indicates that a small fillet is essential to reduce stress concentrations due to stress razors. Knowing that the yield strength value is 450 MPa, this component is left with a safety factor of 1.34. Similarly, a torque of 900 Nm is applied to the shaft. This torque is designed to overcome the friction in the rollers and gives sufficient energy to the pipe to overcome the elastic region and initiate roll deformation. The same boundary condition as the previous shaft is applied, with only the force replaced by the torque. It results in even lower stress of 141.3 megapascals, with a safety factor of 3.18 that is relatively more than enough for this kind of use. A conical part is added to cancel the stress concentration, enabling the part to succeed without excessively thickening the steel plate. This force is distributed among 6 holes, dividing the load equally due to symmetry. The simulation result shows that a maximum of 268.2 megapascals stress occurs as shown in this figure. The yield strength of the material is 470 megapascals, leading to a 1.68 safety factor, which is the lowest safety factor among all components. After generating drawings and cutting lists from SolidWorks, we purchased the material and then started manufacturing the machine. A bandsaw is used to cut the parts like the UPN, bushings, plates, tubes, and other parts. Then lathing process for the shaft housings and caps. They were manufactured with specific tolerances for smooth contact movement. CO2 welding was used for higher strength and higher penetration, and relatively faster process with a lower heat effect than conventional electrode welding. Many more tools were needed for drilling, threading, surface finishing, cutting. Grease was added to the bearings while hydraulically pressing them into their housings. You will now see the slider with the shaft rotating smoothly inside it. Finally, in conclusion, a basic geometry was parametrically designed. This geometry was used for setting up boundary conditions for a simulation to forecast the required force and torque to operate the cold roller bending machine. A complete 3D model was then drafted and continuously modified after testing it in static simulations. The machine has 4 constraints, which are: the machine can bend a pipe with a diameter up to 50 mm and thickness up to 5 mm and radius of curvature down to 100 mm, and finally a bend angle up to 180 degrees. The simulations resulted in a safety factor of 2.65 for the top plate, which was the lowest. However, the most important thing here is how expensive is the machine? The answer is $1,683. Keeping in mind that this machine is eco-friendly, which means no heat addition for bending and no electrical cost. And most importantly, it is manual with an operating force less than 10 kilograms. Besides, this machine weighs 350 kilograms, which is relatively light, thus transportable. The machine was then manufactured and tested. But we could not continue the process because of the current pandemic. Thank you. All simulations, drawings, and reports can be published for educational use. I'll be glad to answer any question. You can email me at kevinjemail@gmail.com.